Imagine a network node compromised not by malware, but by an adversary with a stolen credential, using native administrative tools like SSH or PowerShell. Because the commands are built in, the activity slips right through the perimeter. Traditional network defense relies on semantic inspection. It reads packet payloads, scans file hashes, and looks for known malware signatures. That works for recognized threats, but hunting for malicious code fails when the attacker exclusively uses the system's own authorized utilities. This pattern is known as living off the land, or valid credential abuse. The adversary logs in instead of breaking in. They move through the system leveraging legitimate administrative rights, leaving no recognizable malicious payload for endpoint detection systems to find. When this access is routed over standard administrative channels, or when data exfiltration is fully encrypted, traditional deep packet inspection has nothing to read. The security stack is effectively blind, yet while commands may look legitimate to a security filter, the attacker's lateral movement alters the physical behavior of the network. As they fan out to access new services or stage encrypted data, the underlying structural relationships of the environment begin to warp. An attacker can present perfectly clean semantics, while their actions create a geometry that is inconsistent with the learned pattern of life. PTCP Zero-Day is a defensive architecture built specifically on this premise. To catch an attacker hiding within legitimate channels, it explicitly ignores packet content. It operates as a topology-native system. Instead of tracking discrete user identities or inspecting individual endpoint processes, it monitors the holistic shape of the environment. By treating the network as dynamic spatial geometry, defenses measure structural shifts. They look at the distances, capacities, and relationships between thousands of nodes simultaneously. Viewed through this lens, an encrypted tunnel or a burst of lateral valid credential logins ceases to be invisible. It becomes a measurable mathematical anomaly. The strategy is a complete pivot. We stop trying to identify exactly what the attacker is and start measuring exactly how the infrastructure bends. This diagram outlines the PTCP quarantine architecture of certainty, a 4-layer blueprint translating network geometry into defensive action. At the base, Layer 1 ingests continuous non-semantic signals. It pulls metrics from heterogeneous hardware, like DPUs, eBPF agents, and switches, under a strict constraint. Raw payloads, commands, and secrets are outright rejected by design. None of it enters the scoring path. Instead, telemetry is stripped into dimensionless capacities. This discards sensitive data at ingestion, sidestepping privacy liabilities and data retention risks, while isolating the structural signals required to model the network. Moving up to Layer 2, that raw, normalized data feeds into the mathematical core, converting into spatial geometry. The first crucial component here is the pattern of life tensor train, or PAL-TT. PAL-TT takes millions of multidimensional telemetry data points and compresses them into a baseline probability tensor. It learns exactly how the network should behave. The system then applies an inverse capacity distance mechanic. In this mathematical space, relationships with high trust and high capacity pull tightly together. Conversely, paths that are congested or carry low identity trust stretch further apart. When an attacker executes a living off-the-land attack, like using an admin credential to rapidly fan out to new servers, it creates sharp localized distortions in these established distances. To detect this warp, the core uses the D-topo security formulation. D-topo acts as a geometric sensor. It measures the severity of the structural deformation using curvature gradients and relative entropy drift, identifying an anomaly entirely without reading a malware signature. Long before traditional security tools can decrypt an exfiltration payload, this predictive core has calculated the exact topological blast radius of the threat. That calculation feeds directly into Layer 3, where mathematical detection is translated into functional security optimization. Traditional microsegmentation relies on static, predefined security zones, but real-world compromises move dynamically, constantly crossing those rigid boundaries. As a result, standard automated response often requires quarantining an entire subnet to stop a lateral threat, a blunt action causing production outages. Instead of dropping a static subnet, Layer 3 computes a dynamic minimum cut calculation. It analyzes boundary capacities to find the precise perimeter requiring the fewest possible sever points. It plans to sever only those specific compromised edges, successfully isolating the threat while leaving the remainder of the host's functionality intact. This dynamic minimum cut geometry transforms broad network quarantines into surgical, blast radius limited interventions. Finally, Layer 4 translates these technical containment plans into defensible governance. Security operations teams rightly fear automated quarantine tools. A single false positive triggering a widespread firewall block can take down critical infrastructure faster than the adversary. To solve this, PTCP introduces the geometric kill switch, which operates entirely inside a safe envelope governance framework. By default, the minimum cut containment plan is strictly a dry run. The necessary block is staged, but locked behind a digital approval gate. Active enforcement only triggers when governance criteria are met, like change tickets, dual control approvals, and a mandatory rollback plan. Mathematical evidence allows active network enforcement to be safely gated rather than blindly automated. To validate those governance approvals, the headend generates a comprehensive artifact known as the proof pack. The proof pack supplies deterministic decision hashes, dominant mathematical drivers, and explicit denial reasons. It provides audit and procurement teams with the exact logic behind every proposed containment action. PTCP Zero-Day functions as an intelligence overlay. It calculates the geometry of a threat and passes bounded, auditable action plans to existing EDR, NDR, and firewalls for execution. As attack techniques advance, semantic inspection will continue to lose visibility. Encryption will deepen, and attackers will increasingly use native tools against the network. When adversaries weaponize legitimate credentials and packet payloads go dark, geometric topology provides a measurable signal of compromise that traditional semantic tools cannot see.